Okay, so my name is George, and I'm an engineer at Studio Gobo. We're a game development studio based in the UK of about 120 developers, with quite a bit of experience working in Unreal Engine. And for the last 4 years, I was part of the team working on Hogwarts Legacy, a large open-world RPG built in Unreal Engine 4. And for the last year or so, we've been working on our first full dev project in Unreal Engine 5. So it was while working on Hogwarts Legacy that we experienced a number of challenges working with collision data. And these ranged from small day-to-day frustrations to big uphill battles to fix up badly authored content due to bugs or performance issues. And many of these challenges were exacerbated by the scale of the game. The number of unique assets, the large open world, and even the large distributed development team. So basically, we learned a lot of lessons the hard way. Problems quietly stacked up until they became obvious but were very painful to address. But in the process of tackling these problems, we developed a number of ideas, best practices, and tools for working with collision data in Unreal Engine that we've been able to put into practice on our current project. And today I'm going to be sharing some examples of these problems and those best practices and tools. So this is the structure of the talk. And I'm going to start off with a recap of the basics, a reminder of the fundamentals of Unreal's collision framework. So first of all, what do I mean by collision data? Well, I'm talking about collision geometry, so the actual meshes and primitives in the world, and collision settings, the properties that we have on objects. And together, these define how objects move and collide in the world, and the results that we get back from collision queries. And in fact, collision settings are going to be the main focus of the talk today. I'll also take this opportunity to mention that this screenshot and a number of others in the presentation today are captured from the StackoBot sample game, which you can find on the Unreal Engine Marketplace. So collision geometry is very often associated with a static mesh asset. That geometry can be of a few different types. And then that static mesh gets used in the level in some way, either placed directly or as a component in a blueprint, or even via instance foliage. We also end up using primitive shapes quite frequently for gameplay elements, so trigger boxes for gameplay scripting, and capsules for character collision. And there's a few other ways that collision gets into the world too, like landscapes. So Unreal has a concept of collision channels. So collision channels are a set of distinct types that can be used for objects and queries in relation to collision. So collision channels are split into object channels and trace channels. So the difference between these is that object channels can be used for objects, while trace channels can't. And the engine provides a number of channels out of the box, like world static and pawn, but you can add your own in the project settings. And every component that has collision in Unreal has a collision profile. So a collision profile is a set of properties comprising a collision-enabled enum. Do we have collision or not? An object type, which is a collision channel chosen as the type of this object. What kind of object is this? And then a set of collision responses. So a response, which is either ignore, overlap, or block, to every collision channel in your project. And these responses determine how your object responds to other objects or queries that are using that collision channel. And together, this object type and responses are the basis for collision filtering. So collision filtering is how Unreal decides what should happen when two objects collide using their collision profiles. And it's best explained by walking through an example. Here we have the player character on the left who's walking forwards, and they're going to walk into this bush. And both the player and the bush have collision geometry. So to determine what should happen, we're going to look at the collision profiles of both objects. We look at the player's object type, which is pawn, and we look at the bush's response to pawn, which is overlap. And then we do the same the other way around. So we look at the bush's object type, which is world static, and look at the player's response to world static, which is block. So this gives us two different interactions. We've got overlap and block. And to determine the overall interaction between the two objects, we take the least blocking of these. So in this case, that interaction is overlap. And the player is going to overlap the bush and intersect its collision geometry. And it's not going to be stopped from moving. And to walk through a second example, here the player's moving forwards into this wall. And again, to determine what happens, we're going to look at the collision profiles of both objects. We'll look at the wall's response to the player's object type again. In this case, that's block. And we'll look at the player's response to the wall's object type, which in this case is also block. So because both of these interactions are block, the overall interaction is going to be block, and the player is going to be stopped from moving when they hit the wall. So there are also callbacks which fire when objects move into each other. And that callback depends on the result of that interaction. So in the case of an overlap interaction, there's an overlap event which is fired. And in the case of a blocking interaction, a hit event is fired. Unreal has an interface in C++ and Blueprints for performing collision queries. So collision queries allow you to make sense of the world spatially without moving an object. So a line trace simulates what a ray moving through the world would hit. A sweep simulates what a shape moving through the world would hit. And an overlap test looks for geometry overlapping a particular location. And the behavior of collision queries depends on collision profiles and collision filtering in the same way as movement. And finally, Unreal lets you save collision profiles as a collision preset. So a collision preset has all the same settings as a collision profile, but we also give it a name and a description. So a collision preset can then be referenced on components and static mesh assets to avoid specifying all the collision settings manually. And the engine provides some presets out of the box, like block all, but we can define our own in the project settings. OK, so that wraps up the recap of the fundamentals. I'm now going to move on to talking about managing these collision settings. So first of all, why is managing collision settings a hard problem? First reason is complexity. When you're considering the collision settings for an object, you need to consider how that object should interact with all the other objects in your game. So the example I have here is the player character. You need to consider how the player character collides with the world and enemies and various gameplay elements. But if we're considering projectiles, we need to consider how they interact with the player in addition to all those things. So as your objects, the number of objects scales up, the number of interactions scales up greatly. So the second reason is that in addition to these interactions, we also end up with a large number of different systems that want to use this collision data directly, and mostly via collision queries. So I've got some examples here of common systems that games have that rely on collision queries. So for example, player movement is often the most obvious way that collision is experienced by your player, and Unreal's character movement is built entirely off of collision sweeps. We often use sweeps or traces to position a character's feet on the ground using IK, and we often use line traces to determine if an AI enemy has line of sight to a target. But perhaps the biggest challenge is that while all the users of collision data, like those systems I was just talking about, well, all of those are usually written by programmers, the data is being defined by content creators. So the requirements of the data are being defined by systems, but the developers actually setting up these collision settings are the ones creating new static mesh assets and blueprints and putting them in the world. So these are usually artists and level designers, and collision settings are not necessarily on the radar of all content creators. And in addition, everything gets harder at scale. So bigger games are going to have more content, more levels, larger levels, more unique assets, more systems and mechanics that want to use that collision data, and larger teams too. So that means more data that needs managing, more requirements, and more people who all need to be on the same page about how these collision settings should be used. So one of the mistakes we made when we were working on Hogwarts Legacy was we didn't have a clear plan for how collision channels should be used on our project. And in particular, the purpose of each collision channel was unclear. So that led to confusion. We had confusion amongst programmers about what collision channels should be used for a particular query, and confusion amongst content creators about what collision settings their objects should use. And bluntly, this led to bugs. We had lots of queries and assets which were set up wrong. And then additionally, because of this confusion, we also had too many collision channels added. There's actually a limit on how many collision channels you can add in your project, and we ran out. We had to make a change to the engine to claw back some reserved collision channels. Basically, the result of all these mistakes was we had a lot of code and content that needed to be fixed up retroactively. So how can we do better? Well, the first thing to do is you need a clear definition for what each collision channel is for and what the responses to that channel should mean. So these definitions are going to determine how a channel should be used in code and what the requirements are of your data. So if you aren't certain of these definitions, it's going to be very easy for your code and content to go wrong. And this applies to new collision channels, which you're adding to the project, but it also applies to the ones that are provided by the engine out of the box. So the engine provides some channels, but doesn't clearly define how they should be used, and it's your responsibility to do that as a project. To give an example, the visibility channel I frequently see confused for things which are visible or as a kind of catch-all for things with collision. But it doesn't correspond to render visibility, so what does it mean? Well, the answer is it's up to you. It's up to your project. But I'd suggest AI line of sight if that's a concept in your game. And remember that adding a new collision channel is always a big deal. You're creating a new requirement for all of the collision data in your game. So make sure it's always a well-considered choice and consider some limitation or oversight on who can add new collision channels. So once you've settled on the definitions for your channels and responses, you need to have this information stored somewhere that can be referenced by all your team. So this is an example taken from our current project. This is just a table that's up on a Confluence page, just showing what the channels we're using on our project are, a description of each, and then trying to explain what those responses mean and how they should be used. So this is going to provide useful guidance to content creators who are setting up data, but also helpful for programmers who are writing queries. And having these clear definitions documented is also going to help with maintenance. It's going to be much easier to identify setup errors in content or mistakes in how queries are written when you can clearly see the way it should be used. So another mistake that we made on Hogwarts was, for quite some time, a large percentage of our blueprints and static mesh assets have been set up using custom collision profiles, i.e. not using a collision preset. And this was a big source of inconsistency. We had lots of assets which should have the same settings, but didn't. For example, hundreds of different tree static mesh assets. We just simply had a lot of objects which didn't have the right collision settings that were set up wrong. So to give a kind of contrived, made-up example of why this happens so easily, I've got two tree static mesh collision profiles here, which should be set up the same but aren't. And although you can tell that they're set up differently, it's not obvious which one is correct at a glance, or which one, or how it should be set up. So these inconsistencies and setup errors presented as bugs. And those bugs could be very obvious, or they could be extremely subtle, like a particular tree not blocking AI line of sight. So the other problem with this approach was that when new requirements emerged for a system, for example, a change to how a collision response should be used, or we identified a pattern of error with how a channel was being used, it was very hard to make those changes and fix these things up, because it required changes to a very large number of different assets. And in the end, to fix bugs and ship the game, there was a lot of retroactive work to create and assign appropriate collision presets to existing content. So this tip should be obvious from what I was just saying, but use collision presets. It's perhaps one of the most impactful things you can do to help with managing collision settings on your project. It's going to make it easier for content creators to assign collision settings to objects without error, because they're going to be choosing from a drop-down rather than setting up every setting of the collision profile individually. And it's going to make it easier for everyone to reason about your content and its expected behavior by giving your content a well-defined set of possible settings that it could have. And it's also much easier to spot an asset which is using the wrong collision preset than one which has a single incorrect setting on it. And finally, this is going to make it much easier to maintain and manage your content as you make changes. If you're adding a new channel or changing an expected response to a channel, you can do that very efficiently by updating your presets rather than needing to update large numbers of assets. So a few tips on actually utilizing collision presets. Remember that you can add as many presets as you like. There's no limit, and there's no runtime overhead to having more presets. And when it comes to naming collision presets, you should be naming them based on what you expect them to be used for, not the responses you expect them to have. Remember that the goal is to categorize your content and make it easier for content creators to choose the right preset without thinking too much about the individual responses. And of course, it's just not practical to have a collision preset for every permutation of collision responses. And on a similar note, it's fine to have multiple presets which have the same settings but have different names. Again, your goal is to make it easier for content creators to choose a preset and to group your content in a sensible way. And while the engine does provide some collision presets out of the box, not all of them are a good idea. For example, overlap all, I frequently see used for trigger boxes, but I don't think I've ever seen a case where a trigger box needs to detect everything, particularly when we consider trace channels. And in fact, using overlap all for trigger boxes like this can cause performance issues, which we'll talk about a little bit more later. So we became such strong believers in the value of collision presets that we went one step further on our current project and actually disabled the use of custom collision profiles completely, so requiring that all content has a collision preset assigned to it. So this change was done with just a few lines of engine code, but we included a couple of extra UX niceties as well. So you can see here we've grayed out the custom option to sort of remind people who might be in the habit of using it that it's explicitly disallowed. And then here we've made the collision preset list searchable, keeping in mind that we expect to add lots of collision presets, and we're trying to help the workflow of content creators. And another engine change we made was we exposed collision presets to the reference viewer. So again, this is another way to help us in auditing and maintaining our content as we move to using collision presets more widely. And again, this was done with a few dozen lines of code added to the engine. And something else to mention is that this also included use of the custom collision profile, which allowed us to track down undesired uses of custom from before we disallowed it. So another tool I want to talk about that we've made use of to help audit content is an editor utility widget, which lets you toggle the editor time visibility of actors based on their collision settings. So this gives us a way to kind of visually filter our content. For example, show only objects with a custom collision profile, or show only objects which block enemy line of sight. Or in this example here, show only movable objects, which are often a performance concern that we found is enabled unnecessarily. So this tool has been great for efficiently understanding our content and identifying setup errors at a glance. So to summarize managing collision settings, remember that managing your project settings requires both forward planning and continuous effort. And I strongly urge you to have it on your radar so that problems don't quietly stack up. You need to have a clear definition of the purpose of each collision channel and what each response to that channel means. And you need to have this information documented somewhere. And finally, use collision presets everywhere to reduce the chance of setup error and help your content creators in managing and maintaining content. OK, so moving on from collision settings, I'm now going to talk about collision queries. So why are we talking about queries in the context of this talk? Well, collision queries and collision settings are naturally tied together. There's a feedback loop between your queries and your data. The queries you write are going to define the requirements of your data. For example, what collision preset a particular object should use, or what the object type and responses a particular preset should have. And in addition, your existing data is going to determine how easy and efficient it is to write queries for the results you need. And basically, it's hard to get your data right without getting your queries right, and vice versa. Additionally, there are a number of mistakes I see made working with collision queries, even within experienced teams. So one of those mistakes is adding new channels unnecessarily. And I already mentioned that we had too many collision channels added on Hogwarts. And one of the reasons for this was often a channel was added for a particular purpose where an existing channel could have been used instead. Or a system was using multiple channels where it could have leveraged a single channel more effectively. Another mistake is doing more queries than we need in order to filter data, which is very inefficient. And I also see systems that rely on data being set up in a very specific way or rely on assumptions about the classes of things, these assumptions break over time. But mostly, the most common issue is just queries which are buggy, queries which don't return the correct result 100% of the time. So these mistakes usually stem from a lack of understanding. For example, not understanding how collision filtering works. So collision filtering is key to Unreal's collision framework, but often not fully understood by all engineers working with queries. And in addition, I often see some of the options which are available for configuring queries and the results they return overlooked. And when these options are overlooked, that's often the source of more complicated setups. And finally, I see confusion between the different query functions which are available. So I see confusion about which one should be used for a particular purpose or what the difference is between their behavior. So talking about the confusion between different query functions, one of the reasons for the confusion is just the sheer number of different functions that are exposed in C++ and their naming permutations. And this isn't even all of them, this is most of them. So I'm going to give a bit of a summary now of the different query functions and try and highlight some of the differences between them. So line trace single by channel. This is your basic raycast. So it uses a collision channel and stops on the first bit of collision that has a block response to that channel. So to walk through an example here, we're going to do a line trace on the visibility channel. And the first thing we're going to test against is the player. So we're going to look at the player's collision profile and look at the response to the visibility channel, which in this case is overlap. So the trace is going to continue. Next, we'll test against this wall. And in this case, it has a block response to visibility. So the trace is going to stop, and we'll return a hit against the wall. So note the parallel to movement here. Things are stopped when they hit something with a block response to their channel. And two last things to mention. So query functions have a collision response params argument used for providing responses, and we'll talk more about that in a minute. And the hit information is returned in this hit result struct containing the location, normal, and the component that was hit. So line trace single by profile. The behavior of line trace single by profile is exactly the same as line trace single by channel. The only difference is that we use an existing collision preset to define the channel and responses of our trace rather than defining them ourselves. So for this example here, we're doing a trace by profile using the player capsule profile. And this is just referencing a collision preset we've defined in our project settings. So that means that what we're doing is a trace on the pawn channel using this set of responses. So line trace single by object type. While tracing by channel and tracing by profile have the same behavior, trace by object type works differently. So rather than looking for things which respond to a particular channel, we're looking for objects which have a particular object type. So to walk through an example, here we're going to do a trace by object type with object type pawn. And first we'll test against the player. And in this case, the player has object type pawn, so we're going to return the hit against the player. So notice here, we didn't check any collision responses. And that means that tracing by object type doesn't do collision filtering, which makes it a bit unusual. Collision filtering is the reason we have all these collision channels and responses, and is perhaps the most powerful bit of Unreal's collision framework. So something else to mention is that I often see confusion between trace by channel and trace by object type. I see people say, why is my trace on the pawn channel returning something that isn't a pawn? And I think this confusion is partly down to the naming of the two functions. It's not completely obvious from their names what the difference is going to be. An object type is a collision channel, for example. So just be aware of this source of confusion and always keep in mind the distinction between these two functions. And the last tip is just to think twice before using a trace by object type rather than a trace by channel. We're not doing collision filtering, so we can't opt out of hits on a per target basis. And if you are tracing by object type and finding you need to filter your results a lot after they're returned, for example, by casting, or you find you need to trace against multiple object types in one query. Those are both clues that perhaps you should be doing a trace by channel instead. OK, so line trace multi by channel. So this is very similar to line trace single by channel in that we're using a channel, and we're going to stop on the first blocking hit. But in addition, trace multi by channel returns all the overlaps which were detected along the way. So that means it can be used to detect multiple things in one query. So I'll walk through an example here. We're going to do a trace multi by channel with the visibility channel. The first thing we'll test against is the player, who has an overlap response to the visibility channel. So we'll register this overlap, and the trace will continue. Next, we'll test against this wall, which has a block response to visibility. So the trace will stop, and we'll return the hit against the wall and the overlap against the player. So there's also a test version of each of the traces I've talked about, tracing by channel, tracing by object type, and tracing by profile. So this is the same as line trace single in its behavior, but it returns only true or false, indicating if we hit something and not the full hit information, the location, the norm, or the component that was hit. So there's some work saved here in not extracting and constructing that hit info. So it's a slightly more performant choice in the case. You just need to know that there was a hit, not necessarily what it was. And finally, there are sweep equivalents of all of the line trace functions that I've just been talking about. So these have the same behavior as their line trace equivalent, but they sweep a shape through the world rather than tracing an array. And to kind of summarize all those different functions that I've just been talking about, here's a matrix which tries to show that underlying structure behind the different naming permutations. So we can be doing a line trace or a sweep, and that can be by channel, by object type, or by profile. And then that query can be single, multi, or test. So moving on then, I want to talk a bit about that collision response params argument that I mentioned earlier. So when you're tracing by channel, we aren't just looking for things which block that channel. Just like a moving object, our query has both a channel and its own set of responses, which are going to be used for filtering. So the default collision response params argument that we pass has a block response to everything. So for example, when we were doing that trace on the visibility channel, we were actually passing these block responses to every other channel, and we were just doing regular collision filtering with, when we were testing against each of these objects. So this is something that I find is often overlooked. People assume that a trace is fixed to only finding things that are set up to block their channel. But you can modify these responses, which can be quite useful. And to show what I mean, I'll give a couple of examples. So we had a case where some IK traces that we were using for the player were occasionally catching against other characters. So to fix this, we just updated the traces we were doing to ignore the pawn channel. And we could have done this instead by updating all our different character collision presets to have an ignore response to our IK channel. But the solution we chose didn't require any data changes, and it was a bit more robust. We knew the problem wouldn't come back. For a second example, imagine you have a case where you're using a weapon collision channel for hit scan weapons, and your enemies are configured to block this channel. So you want to add a new weapon which can shoot through multiple enemies. And you could do this by adding a new collision channel and setting up your enemies to overlap this new channel so they can be detected using line trace multi. But instead, you can just change your trace to have an overlap response to pawn, which means your query is always going to have an overlap interaction with your enemies. So we can use line trace multi to detect multiple enemies, and we didn't need to add a new collision channel at all. So I want to share a tool that we've written, which has proved helpful in the past. So this is a simple actor which performs collision query on tick, and debug draws the result. And most importantly, it can be configured via the properties to perform any possible collision query. And shows much better in a video, so that's what I've got. So this is just inside the Lyra sample game, and I'm showing how we can dynamically configure that query function and the parameters and what the result looks like. So here I'm switching it between doing a trace versus a sweep, switching between tracing by channel and tracing by object type. So I've used this personally for testing a query before writing it, or understanding the collision settings of real content, or just debugging a specific problem. But I've talked a lot about confusion and misunderstanding amongst programs, so I also see this as a useful educational tool. And something we added for that tool were some debug drawer helper functions for swept shapes. So it's very easy to add debug drawer for a line trace, but a bit harder for swept shapes. And so by adding these on your project, you'll lower the barrier for other programmers to visualize and debug their code that's using sweeps. So a couple more tips. The blueprint interface for collision queries is more limited than the C++ interface. In particular, you can't configure collision responses directly on a query. So while you can trace by profile, remember that collision presets are restricted to only using object channels for their object type. So if you're doing a trace by channel from a blueprint, there's no way to configure your collision responses, which I've just given a couple of examples can be quite useful. And a pet peeve of mine, please don't use the blueprint interface in C++. In addition to this limitation I've just mentioned, it adds another query function variation which programmers have to parse, when there's already enough of them to have confusion. And one very common use case for collision queries is tests for things which a character will collide with or has to stand on. And I frequently see these being done with just a single line trace on the pawn channel or even on something else like the visibility channel. And we usually end up with bugs down the road where the behavior of the test has a discrepancy with the behavior of the character. So if you're doing a test for movement blockers, then you should probably be using the character capsule's collision shape and collision profile. And if you're testing for the ground, i.e. somewhere for the character to move to, or teleport to, or respawn, then in addition, you should also probably be testing if that hit is walkable, i.e. not too steep. And to do that, you'd be implementing logic similar to what you find in character movement component. OK, so to kind of summarize what I've said about collision queries, remember that your queries and your settings are always linked, and it's going to be hard to get one right without the other. There are some common sources of misunderstanding that I've talked through that can lead to bad decisions when writing queries, which you should be aware of. And there are many different options available when writing queries that you can utilize to write them more effectively. So for this next section, I want to give a couple of in-depth examples of how we've used collision settings and collision queries together. So the first is player-only collision. So it's quite a common requirement to have an invisible wall that only the player will collide with, and not enemies and projectiles. And you could do this by giving the player a special object type, but that could be challenging if you have lots of existing content, and it introduces a difference between the player and other characters when the majority of your content is going to want to respond to this channel in the same way as it does to pawn. So instead, you can achieve this without changing the player's object type by taking advantage of collision filtering. So what you want to do is create a new player-only object channel. And this is going to represent objects which only affect the player. And here we've set the default response to ignore. So that means that existing collision presets and newly added collision presets are going to ignore this channel by default, which is what we want. So then we'll set up the player's collision preset to block this channel. And then finally, we'll add a new collision preset for these invisible walls. Here I've called it block-only player. And this uses the player-only channel for its object type, and is set up to block pawn. So then, using collision filtering, we end up with a block interaction between the player and this new preset, and the player is going to be blocked by these walls. But the key is that because only the player is set up to block this player-only channel, only the player is going to have a blocking interaction, and everything else is going to have an ignore interaction with these walls, including other pawns. So using player-only collision like this actually introduces the opportunity of a big optimization. So it's very common to have trigger boxes which should only trigger their logic when the player walks into them. And this is very often done by having the collision box set up to overlap everything, and then casting to player or doing something similar to that when an overlap event is received. And this is an easy mistake to make. Trigger volumes and shape components are usually set up to overlap everything by default. But this is actually very bad for performance. And that might not be obvious until you already have thousands of trigger volumes set up like this. So we can do this better using an overlap-only player preset for our trigger volumes instead. So like the previous example, we're using the player-only channel as the object type. But now we're set up to overlap pawn rather than block. So this is going to overlap the player character, but ignore everything else. So this is going to be more performant. We're filtering out things which aren't player with just a few bits of data rather than a callback into gameplay code and a cast. But even more key is the fact that collision filtering is done at the broad phase of collision detection during queries and movement. So now we're going to be skipping a lot of expensive testing of collision geometry every time anything moves. So the next case study I want to talk through is a third-person camera. So a couple of requirements we have of a third-person camera are we want to avoid clipping inside geometry, and we want to avoid geometry coming between the camera and the player. So we did this on Hogwarts by sweeping from the player to the desired camera location to detect geometry, and then pulling the camera in if we hit something. And this depended on objects using a block response to the camera channel. But a problem we had when implementing this was it was very jarring for the camera to pull in or cut when a tall, thin pillar came between the camera and the player. And we couldn't just set these pillars up to ignore the camera channel, because we still needed to prevent the camera from clipping inside them. So our solution was to use the overlap response. So we used the overlap response for these pillars to mean something which we should avoid clipping inside, but which we could still allow to come between the camera and the player. So we continued to sweep for blocking geometry, but we also added an overlap test at the camera location. So this is a great example of a non-physical collision response. So it doesn't affect movement, but it does affect queries and the behaviors built on them. And you can make use of this kind of idea when writing queries. OK, so wrapping up, I've talked through some of the problems we had with collision settings. I want to briefly mention a couple of other areas related to collision that we spent a lot of effort on while building Hogwarts. So performance is a huge topic. Movement, physics, and queries were always very high up in the profiler, and streaming time and memory usage of collision were also considerations. We spent a lot of time on finding effective ways to profile and optimize these. We also made a lot of content changes to reduce their costs too. In addition, we also spent a lot of effort on character movement. So specifically, how Unreal's character movement implementation and metrics interacted with the kind of collision geometry we had in our game. And again, we had to make both code and content changes to improve the quality of character movement. So basically, these are areas which should be on your radar when you're thinking about collision for your project. OK, so the last thoughts I want to leave you with are you should be thinking about how to manage your collision settings in a proactive way. You should make sure your team have a good understanding of collision queries and Unreal's collision framework. And there are lots of best practices and tools that you can use to help you with this. And the biggest takeaway is, I hope you'll agree, doing all of this is worth it to save yourself a lot of time and effort in the long run. Thank you very much.